Hello, everyone. Good afternoon. I'm back with a lecture on groups, or more precisely, group convolutions on homogeneous spaces. So that's a bunch of jargon right there, but we'll see exactly what this means. So in the previous lecture, you heard about convolution on grids. And that is, of course, the most common situation in deep learning when people use convolutional networks for images or 3D volumes. Usually they're doing some kind of convolution. But what we'll look at in this lecture is how to generalize this from convolutions that are equivariant to translation to convolutions that can deal with more general groups of transformations, including mainly rotations, rotations of planar images, 3D volumes, spherical signals, and in fact, a far more general class of groups and spaces on which they act, called the so-called homogeneous spaces. So after looking at some examples, I'll give you a high-level idea of the general theory that's been developed for these kind of convolutional networks. And at the end of the lecture, I'll talk about an even further generalization to so-called induced representations in steerable CNNs, which geometrically you can think of as convolutional networks that have as input, output, and also as internal feature spaces spaces of fields on a space, things like vector fields, tensor fields, and so on. And what I'll come back to multiple times in this lecture is the convolution is all you need theorem, which says basically that when you have a feature space that's a space of signals or a space of fields on a homogeneous space, then the most general kind of equivariant linear map is indeed a convolution of a generalized kind. Okay, so let's get started, and we'll start with a very simple example, and also the first one that was published about in the deep learning literature. So the idea here is, let me get out my pointer. Right. So the idea is we have an image, and just like in the case of grids and translational convolutions, we can take a filter, say this little patch containing an eye-like pattern, and we can convolve it translationally over our image. So we're going to translate the filter, and at each position compute some kind of inner product, some kind of match between the filter and our image, and we'll register a response. And in this case, you see, well, this eye detector filter, it fires, of course, in the position of the eyes, and that's a translational convolution. We can do it with any number of filters, so we can have an eye filter and a mouth filter, which fires here in the green spot. We can have any number of them, just as in a standard CNN. But now what we want to do is we want to increase the weight sharing. We don't just want to use the same filter at every position. We also want to use the same filter in different orientations. So we want to apply a rotation. So that's indicated in this figure here at the top. We rotate the filter. In this very simple case, we'll just rotate by 90 degrees. And we get an eye detector for vertically oriented eyes. And when we convolve it, of course, at least in this sort of simplified cartoon picture of what could happen, it doesn't fire at all, because the eyes here are in the horizontal orientation. It's an upright face. So this feature map doesn't give us a big response. And similarly, when we rotate by 180 or 270 degrees, we don't get any big responses as we did in the upright orientation. But of course, you can see that when we rotate the input image, then those might start to fire. So what we've achieved here, first of all, is increased weight sharing. So whereas in a standard translational CNN, you might need to learn the same filter in different orientations. Here, this is automatically this is built in. And in cases where the data has rotational symmetry, that's a very useful thing, as has been shown many times in empirical results. For example, in medical imaging, where medical tissues might appear in any kind of orientation. Now, what we've been emphasizing in this course is, of course, this notion of equivariance. So let's see if this operation that we've defined is indeed equivariant. So we'll take our image and we apply a transformation, 90-degree rotation. Again, this is just a very simple example. We apply an element from our group, the 90-degree rotation, and then we apply the same operation. So again, we're going to take our two filters. In general, could be more, but here we have two filters. Apply them translationally, rotate them, apply again translationally, etc. And we generate 2 times 4 feature maps. Now, what you can see is that when we apply the upright eye detector, it's not going to fire because now the eyes are in the sideways orientation. However, the rotated filter is now going to pick up on that. So we see now firing in this orientation channel, as we call it. So when we look at what happened as we go from the top right, that's the feature response to the original image, to the bottom right, that's the feature response for the rotated image, we see that we can describe this transformation, this downward arrow here, as in 2 steps. Basically, here we have these responses on a horizontal line, and here we have it on a vertical line. So the first thing that happens is that all the channels, they will undergo a rotation, in this case 90-degree rotation. But another thing happened, right? Here we had firing in the theta equals 0 orientation channel, and here we have it in the theta equals pi over 2 or 90-degree rotated channel. So in addition to the spatial rotation, there's a cyclic shift along these 4 orientation channels. So what was originally theta 0 goes to pi over 2, what was in pi over 2 goes to pi, what was in pi goes to 3 pi over 2, and what was in 3 pi over 2 goes to 0. You can try to visualize this mentally or do some calculations on a piece of paper to convince yourself that this is always true. And now this is a very general pattern that we'll come back to again and again in this lecture, that the types of group actions which we find in the feature space are, first of all, different from what we find in the input space. In the input space, we just take the RGB channels, and each of them is rotated independently, and there's no interaction among the channels. What happens in the feature space is that the channels are rotated, but there's also this cyclic shift. And so that's quite interesting, and it also helps to motivate the geometric deep learning blueprint that we've talked about, and that is the sort of the backbone of the book, the proto book that we have on archive on geometric deep learning. Different group action for each feature space, and here you see how that sort of emerges quite naturally from a simple idea of rotating filters. Same group, rotations and discrete translations, but it acts in a different way in the different feature spaces. So we've verified that this operation is equivariant, but we've only defined it for the first layer. So now we can think about how to create deeper networks with this basic idea. So what you see on this figure is essentially the same thing as on the previous slide, but visualized slightly differently. So here we have again our input image. We can also have a rotated version of that input image. We have a filter here, which we convolve with the image to produce one feature map, and then we rotate it, produce another one, another one, and another one. And of course, we can do the same for the rotated image. And then again, you see that the way the 2 stacks of feature maps are related on the top and bottom is that the each channel is rotated and the channels are cyclically shifted. Now, what we're going to do for the second layer and higher layers is to apply the same general idea. Namely, we're going to take a filter and rotate it 4 times and then convolve it. But now rotating has a different meaning because the feature space transforms in a different way. It has a different group representation associated with it. So in the second layer, first of all, a filter indicated here in the center has 4 channels. In any kind of convolutional network, a filter will have as many channels as the input feature maps that you convolve with. In this case, we have 4 orientation channels. So our filter has also 4 orientation channels. So we can convolve such a filter translationally with this stack of 4 feature maps to produce 1 output feature map. But then, according to the same philosophy as we used in the first layer, we're going to rotate this filter, and rotation means rotating each channel and cyclically shifting them. And what you can see is that if you do this, you get 4 filters, so 4 output feature maps. And again, you can see that the whole construction is equivariant. So if you rotate the input feature map, you apply the first layer group convolution, and then the second layer group convolution using this procedure I just described. You get 4 output channels, which are related to the 4 output channels produced from the unrotated image in the same way, namely rotating the channels and cyclically shifting them. And finally, what you can then do is you can do, for example, this is just an example. You can do many things, but you can iterate this a number of times, have many layers of convolutions, and then at the end of the network, you could do some kind of pooling. So what you can do is you can, in the simplest case, you would just sum over the 4 orientation channels to produce 1 number or an average, or maybe you take a maximum, whatever you prefer. And as a result, you get 1 channel as output. You can see that when you do this, the output will again be equivariant, but it will transform in exactly the same way as the input. So there's no more cycling between channels. There's just, if you rotate the input image and compute the output of the whole network after pooling, you get just the same thing as you get for the original image, except it's rotated. And you can see that that must be the case because cyclically shifting along the channels will just permute the 4 values that you're summing. And of course, the sum, adding a bunch of numbers, doesn't depend on the order of those numbers. Okay, so how can we understand this from the perspective of our general geometric deep learning blueprint? So in the input, we have a signal on some on our domain omega, which in this case is Z2. That's the grid extended infinitely consisting of pairs of integers. Of course, in practice, it's a finite grid, but we sort of imagine that it extends infinitely far with padded with infinite amounts of zeros. And so mathematically, it all works out. Right, so that's our base space omega, and as we'll discuss in more detail later, the way that these feature maps transform is called it transform as a scalar signal. So we have here 1 channel that's a scalar at each position. And if we rotate this channel, we don't have any action on the channels. It's just a rotation as you're used to. And then for the first layer and also higher layers, the way we can think about this is that our domain, omega, now becomes the group. In this case, the group is called P4. That's the group of integer translations, discrete translations, and rotations by multiples of 90 degrees. So basically, if you look at these 4 channels, every pixel in any one of these channels, you can index it by saying, well, which channel is it? So meaning which of the 4 rotations does it correspond to? And then what is the spatial position? That is to say, what is the translation? And so indexing by rotation and translation, that's basically indexing into this group P4. And so in a very general case, the feature map after the first layer of group convolution will be a function on a group. So omega becomes equal to our group. And then a signal on the group transform according to what is called a regular representation. And we'll look into more detail mathematically what that means. But this is just to introduce the nomenclature. And after pooling, of course, our domain again becomes the plane or the grid, Z2, and we have a scalar signal, just like in the input space. All right, so let's try to understand mathematically how group convolution works. And let's do that by making an analogy to the usual translational convolution. So in translational convolution, the idea is, of course, that we have a signal, an image, say, and we have a filter, and we're going to translate the filter and compute an inner product. And then we'll store the result of this inner product in a cell of the output feature map that's associated with the translation that we applied. If we translate by 5 pixels along the x-axis and 10 pixels along the y-axis, compute a dot product, then we'll take that cell 5, 10 and store the output of the inner product there. In the group convolution case, the idea is very similar, but we replace the word translation by transformation. That is to say, we apply not just a translation, but an arbitrary element from our group. So we have a signal, our filter, and then for each transformation in our group, we apply that transformation to our filter. We translate and rotate it, for example, compute inner product, and store the result of the inner product in the cell of the output feature map associated now with the transformation that we applied. And so that's how you see that the result should indeed be a function on your group of transformations that you're considering. All right, so mathematically, we're going to unpack this. And the first concept to unpack is, of course, this concept of translation or transformation applied to our signal or to a filter. So we have here, just to remind you of the notation, we have a signal x on our domain omega. U is an element of omega, so we can index our signal x at the point u. Then we have a translation v, and this translation acts on the signal via the representation rho. And if you recall from the third lecture, the way that works is that the v translated version of the signal x indexed at u is equal to x, the original signal, indexed at u minus v. And there's a very, completely analogous equation for a general group. So the only thing that changes is that now G is an element of our group. And when we apply it to our signal and then index the signal at U, that's going to be given by the original signal indexed at G inverse U. This is just a mathematical way to say, shift and rotate, or whatever the group may be, your signal. Then we have the concept of inner product that we have in our definition of convolution. So in the classical case of a discrete grid with some number of channels C, the inner product between a signal X and another signal, let's say a filter Y, is given by summing over all spatial locations and summing also over all channels. The product of one signal at this position and in this channel times the other signal at this position in this channel. And again, this was already covered in lecture 3, but in general, when we have a signal on some domain omega, we can define an inner product for such signals by integrating over the domain. In the case of a discrete domain omega, that would be a sum. In general, it will be an integral with a certain invariant measure. And then at each point, we take the inner product of the feature vectors along the channel dimension for X and Y at that position, and we integrate the whole thing. And this gives you a valid inner product that we use to do pattern matching. And then convolution and group convolution is defined as followed. I should say that in the deep learning literature, everybody calls this convolution, even though in some other fields it's more common to call this a cross correlation, but we will not be worrying about the difference here. So the idea is the signal convolved with a filter psi evaluated at V. So V is a translation. So we're evaluating the output at a certain translation or a position in the plane, is the inner product of the signal and the transformed filter, the translated filter, which, if we expand the definition of the inner product, is a sum over positions and channels of the signal and the translated filter. And for group convolution, we have something completely analogous. We have our signal convolved with a filter, evaluated now not at a translation, not at a planar position, but at the group element G. That's the inner product between X and our filter transformed by G, which again, we can expand the definition of the inner product and the transformation of the filter, and we get this equation here. And in both cases, using completely analogous derivation, you can show that this mathematical operation here is equivariant, meaning that if you apply a transformation G to your input signal, then you get also that's equivalent to just doing the convolution with the original signal and then transforming the output. Now, one very nice thing to note here is that this whole setup works no matter what your space omega is, and in particular, it also works when omega is the group itself, as we saw happens after the first layer. So you could have X being a signal on the group, so now U is a group element, and then the transformation of a signal on the group is still given by this equation, where we now have G inverse U. That's now the composition operation in the group, and then the whole the rest of the setup still works. It's still equivariant, and indeed that is a mathematical way of saying what, or let's say this setup specializes to the case I just explained for the roto translation group in a more intuitive way. All right, so we studied the group convolution, and I mentioned already that the way that the feature maps in a group convolutional net transform is called the regular representation. So let's look a little bit more detail what that means. Recall that signals are functions. X from omega our domain to C, some vector space, and they transform according to this equation. We've just seen it on the previous slide. And what I was also already mentioning is that in the case where omega is the group itself, as we have in the second and higher layers of a group equivariant net, you can take this G inverse U to mean the left action of G on itself. So if you have, instead of U, you have an element H, and you want to apply the transformation G to it, you just use the composition operation of the group. And you can verify that this also satisfies the axioms of a group action. So this is a valid group action, and it fits into the framework. It's just a special case where omega happens to be equal to the group G. And then this way that the signal transforms is known as the regular representation. So we have our X, that's a feature map. Now it's a feature map on the group G. For example, as we saw before, for every translation and rotation, we have a certain value, certain feature response. The way that we can transform such a thing using a group element G, say again, a rotation and translation, is to just index the original feature map at G inverse X. So let's look at how that general definition specializes to the case that we've been studying of discrete rotations and translations. So to make it less abstract, to actually be able to do concrete computations, we're going to encode our group elements G as matrices. And because the group that we're dealing with here is the group of discrete translations and rotations, the matrices are indexed by a rotation R, either 0, 1, 2, or 3, corresponding to 0 degrees, 90 degrees, 180 or 270 degrees, and a translation in the grid, Z2. And the way we construct the matrix is like this. We have here in the top left a rotation matrix that rotates by R times pi over 2. We can also write that here as a 2 by 2 rotation matrix, capital R of lowercase r. And then we have here our translation in the X and Y direction, which we also can encode here as a two-dimensional vector in this block matrix. And you can verify that when you compose matrices like this, that's the correct way to compose rotations and translations. You might have seen this in a computer vision class, for example. And you can also see that if you apply this to a two-dimensional vector with an added 1 as a third component, this gives the correct way to transform a two-dimensional point in the plane. Now, in the definition of the regular representation, we have two kinds of operations that play a role. The first is the group operation. Well, in that case, for this encoding of the group elements, it's just matrix multiplication, and you can, do the linear algebra here and work with some rules for the sine and cosine. And you can verify that when you compose these matrices, you get this matrix. So the rotation angles, they add up modulo 4 because they get wrapped in the sinusoids. And the way the rotations and translations compose is then that the rotation of the first group element acts on the translation of the second one, and then you add the translation of the first one. It's just a matter of linear algebra. You can verify this, and also verify that indeed, if you apply this roto translation and this roto translation to a point, that's the same as applying this combined roto translation. And similarly, you can do an exercise to verify that the inverse of this matrix is given by this matrix, which is again an element of this group. Then we look at the definition of the regular representation. So now we have our signal. Signal is a function on the group. In this case, that means it's indexed by a rotation 0 to 3 and a translation in the grid. And let's say we apply just a pure rotation to it with no translation, just to keep things simple. Then you can use these two definitions or these two results here for what it means to compose and invert group elements to derive that this transformed signal is given by the original signal indexed at r minus r prime mod 4. So that's how your cyclic shifting along the channels comes in, and how the spatial dimension is affected by this rotation. So that's how, the thing we saw on the very first slide, how that emerges as a special case of a regular representation. Now, this is, of course, a more complicated way to think about it, but the nice thing is that this regular representation is a very general concept that applies to many situations, and that indeed there's a large mathematical literature that proves all sorts of results about these things. So it's nice to see that the thing we already understood can also be understood in this more general framework. And indeed, you can generalize it to all sorts of other groups. So here's one example, the group of discrete rotations in 3D. So let's say you have a three-dimensional voxel grid. Maybe you have some MRI brain scans, and you want to do some kind of learning on it to segment different brain regions or classify certain disease states or whatever it may be. Then you can use, say, a 3 by 3 filter in a convolution layer. And we can apply the same idea. We can rotate this filter using discrete rotations, just to keep it simple. But actually, you see already in 3D, there are many ways to rotate your filter. In fact, 24 ways, if I recall correctly. And that is, in a way, it's good news, because it gives us a lot of weight sharing, and so a lot of statistical efficiency. We're going to need fewer examples to learn from. Of course, it also has a computational cost. That's something we'll talk about in a minute. But the other interesting thing I wanted to mention here is that whereas in the simple case of two-dimensional discrete rotations, you get simple cyclic shift along the channels. What's indicated by this diagram is that these group elements in 3D are related in a very intricate pattern, and so instead of a cyclic shift, you get a fairly complicated permutation for each rotation that you might apply. So the channels undergo this permutation that's indicated by the arrows here. Okay, so we already sort of convinced ourselves that just intuitively that the group convolution for the special case of discrete rotations and translation, that should be equivariant. But let's verify it mathematically, or see how we can prove that in the general case. So we have our input. That's going to be a signal on the space omega-1. Could be, for example, the plane, or we'll later look at an example of a signal on the sphere. And we have here again the equation that tells us how this signal transforms. And we saw that the output of the first layer group convolution would be a signal on the group itself. And again, a very similar equation that tells us how such signals transform. In later layers, we will want to define a group convolution that takes a signal on G and produces as output also a signal on G. And we can give a proof that is independent of the specifics of the space omega and group G. The key insight is that matching a signal X with a transformed filter, as we do in the group convolution, is the same as matching the inverse transformed signal with the original filter psi. So that's given by this equation: X inner product rho 1 G psi equals rho 1 G inverse times X with psi. And this is actually something you need to show, and it depends a little bit on the properties of the integration measure, where you need to use one that has some invariance property called the Haar measure. But this is all quite technical. We will not go into it here. But if you're curious, you can use these words to look it up. And also our proto book has some information on this. Now, using this key insight, we can then show in a few lines that indeed the group convolution is equivariant. So we have our signal X, we apply a transformation by H, and then we convolve with psi, and we index the output at the element G. Now, by definition of group convolution, that's just an inner product between our input, the transformed X, with a G transformed filter psi. And using this result, we can take this H to the other side, and now we have that this is equal to our signal X inner product with the filter transformed by H inverse G. And this is just the group convolution of psi and X indexed at H inverse G. And that is nothing else than the transformed version, the H transformed version of our signal psi convolve with X. So that's the proof that group convolution in the first layer and also the higher layer version of it is equivariant to the action of the group G. Now, we've shown that group convolution is equivariant, but we can also reverse the question. We can say, let's say I have a signal on a space omega, and we know how that transforms, and we have an output signal space on maybe another space omega, or on the group G, or whatever. We have a definition for how that transforms. And now I want to design a linear layer with some learnable parameters that should be equivariant with respect to these representations. And now you can show that if you're using, if the group acts on these spaces in the way that we've just described, by shifting the signal over the plane, or shifting it over the group using the regular representation, then any such linear equivariant map between these regular representations is going to be a group convolution. And of course, there are many technical details that would have to be mentioned. And if you're interested in this, I would recommend having a look at the literature cited here at the bottom. But that's a pretty cool result, because it tells us that in a way we don't have to come up with anything new, at least at a fundamental level, because as soon as we have decided that we want our feature spaces to transform according to a regular representation, if we think that they should be signals on some space, then the group convolution is the most general thing you can do. Now, there are certain downsides in terms of computation for very large groups, for which we've developed this steerable CNN framework that we'll talk about in a minute. But still, it's nice to know that by using group convolution, we're not imposing any kind of unnecessary constraints on our linear layers. So there's you can then think about, okay, how do we implement this, right? So far we've been talking mostly about the mathematics, and I like to emphasize this because the mathematics is still going to be the same in 100 years from now, and the implementation details for how you actually compute this is going to depend on the hardware, and there's going to be trends and different ways of doing that. That change over the years, but still, it's very important, of course, to know about that. How can we implement this group convolution for the very simple case again of the discrete rotations and translation group P4? So what we'll have is we have a set of weights. Those are the filters in their upright position, and then we have a set of indices that we can use to basically create copies of the filters in different orientations. So we create one copy in the upright orientation, one in the rotated, or in all four rotations basically, and that's the operation we call filter transformation. So now we get an expanded set of filters, and those we can just feed into the conv2d operation that you also use in a standard planar CNN. Apply that to the input feature maps, and we get our output feature maps. And so that's a very here's a visualization of how that works. We have our 4 input channels for the filter corresponding to the different orientations. The filter transformation uses some indices to create the copies of filters rotated and cyclically shifted, as you see here in the different rows. And then this is a filter bank that we can just apply in conv2d. So at least for this very simple case, there's very little computational overhead relative to a standard 2D convolution. Because the only extra operation we have to do is this filter transformation. Of course, if you this filter transformation does produce more filters, and so the conv2d operation will be heavier, unless, of course, you reduce the number of free parameters that you're using, which is often a good thing to do, so that you get better performance. But you can also choose to use the same number of parameters, and you have more filters, and you get better accuracy at a higher computational budget. Now, there are many other approaches that have been developed. So first of all, there's the steerable CNNs that we'll talk about in a minute. This allows to address some of the computational issues that you run into for very large groups. There's various other ideas like B-spline CNNs, where you define continuous filters via B-splines on the so-called tangent space of a Lie group. Lie conv, there's a work on scale equivariance, and recently what's been quite popular is equivariant transformers of various kinds. And I should say that this is only a tiny sampling of the literature, but there's a lot of work that you can find on equivariant convolutional networks and other equivariant networks. So one other case study that's interesting to look at is spherical CNNs. So this is useful if you have data that lives on a sphere. So for example, in the Earth and climate sciences, the Earth is a sphere. You might have some data like temperature fields or fields of wind direction at every point on the Earth. And you might want to apply some kind of analysis, some kind of machine learning model to it. Or you might have a omnidirectional camera on a robot, and that's again a signal on the sphere. And when you have a signal on the sphere, again, according to our geometric deep learning philosophy, you want to think about what is the symmetry of the sphere. Well, those are three-dimensional continuous rotations, and you want to build layers that are equivariant to those. Now, I'm not going to go into detail here in the interest of time, but you can define a convolution on the sphere that is completely analogous to the case of the plane that we looked at before. You have a signal on the sphere, a filter on the sphere, and a convolution is defined by taking an inner product of your signal on the sphere and the rotated version of your filter. And now, just like before, the output is a function not on the sphere, but on the group, in this case, the group SO3, the rotations in 3 dimensions, whereas the sphere is 2-dimensional, this is a 3-dimensional manifold. So your output feature map is a signal on SO3. And then you can define a group convolutions for signals on SO3 as well, using, again, the same kind of recipe. Yeah, so this is just saying what I just mentioned, different domains. There's ways to implement this using Fourier transform. Very complicated, so I won't go into it. And actually, this was the way we implemented it in the our first paper on this topic, but it's quite complicated, so I wouldn't necessarily recommend the spectral approach for this type of method. Although Rizi Konder and others have found practical ways to do this. If you just want to implement a group convolution, I wouldn't recommend this, but there are spectral spherical CNNs that work well. So yeah, many approaches to spherical CNNs. You can use, for example, graph convolutions, the spectral spherical CNNs that I mentioned, and again, this is just a small sampling of the literature. There's many approaches. Okay, so we've covered a few examples. We looked at translational convolutions in the last lecture. We've looked at how to generalize that to include discrete rotations. We've seen that in 3-dimensional grids, and we've seen spherical CNNs, and we've seen some general patterns emerge. And what I'm going to do now in the time that we have left is to just sketch a little bit the general theory that describes all of these, where the common theme is that you have a group of symmetries and acting on some homogeneous space. We'll say what that means. Your signal space is a space of functions on a homogeneous space. The equivariant maps that you're interested in are generalized kinds of convolutions. So what are homogeneous spaces? So we recall from our blueprint, we have our domain omega, that's always a set with a group action. So we have a group element G, and if we apply it to a point in omega, we get a transformed point in omega. And for this to be a group action, it has to satisfy certain properties that we covered in previous lectures. Now, if this action is transitive, then omega is called a homogeneous space for G. So what does that mean? To be transitive, well, if we have any 2 points, U and V, in our space omega, then there should exist at least one group element G such that applying G to U gives us V. So let's look at a few examples of homogeneous spaces and also counterexamples. So if you have our domain omega, the plane, then if we take any 2 points, let's say this one and this one, then is there a transformation, that is to say a translation that takes one into the other? And the answer is, of course, yes. For any 2 points, there's a translation that maps one to the other. We can also consider the same example for another group, namely the group of translations and rotations. So we have the same space, and it is also a homogeneous space for the group of translations and rotations. Again, because if we have any 2 points, we can find some roto-translation that maps one into the other. For example, just a pure translation, and maybe combined with any rotation around the resulting point. Similarly, for the sphere, if we have any 2 points, we can always find a continuous rotation that maps one to the other. So the sphere is a homogeneous space for the 3D rotation group SO3. Now here on the right, you see a counterexample. If we have the plane, but we consider as our group of symmetries only the 2D rotation group, so rotations around the center of the plane, around the origin, then of course, if you have any 2 points that have the same distance to the origin, we can rotate one into the other. That's indicated here by these circles. But points at different distance to the origin, they cannot be mapped into each other by a rotation. So this space splits into these orbits, these circles, whereas in other cases there's only one orbit. All the points can be, any point can be mapped anywhere else in the space by an appropriate symmetry transformation. So those are homogeneous spaces. Now, something very important structurally about a homogeneous space is the so-called stabilizer subgroup. So we have our set omega, and we assume that this is a homogeneous space for some group G. Then the stabilizer subgroup of a point in omega, let's say this point in the plane, is the set HU. That's the set of group elements in G that leave U invariant. So if you apply G to U, you get back U. So let's look at examples. Here we have the plane, and if we take our group G to be the translation group R2, then it has a trivial stabilizer, because any translation that we apply, except for the identity, will move this point away. And so only the identity transformation, that's a one element group, a trivial group, only that leaves this point invariant. However, if you consider the group SE2, that is continuous rotations and translations acting on the plane, then the stabilizer is the group SO2, the group of two-dimensional rotations around this point. Any translation will move it away, but any rotations around this point will leave that point where it is. So that's the stabilizer of this point if you consider this a homogeneous space for the group SE2. And similarly, the sphere is a homogeneous space for the rotation group SO3. And if we take any point, then we get a group of rotations around the axis through that point. That's a group called SO2, rotations around the axis. So that's the stabilizer of that group. Now you can show various things. First of all, that this is a subgroup. That's a good exercise. So you look up again the definition of a group, and you check that this set satisfies those, that the identity is in it, composition is associative, there's inverses, etc. And you can show that the stabilizer of any point U, whichever one you choose, is going to be the same as an abstract group. And that's also why these spaces are called homogeneous. Every point kind of looks the same. Now, the key thing to remember is that a homogeneous space is completely characterized by its symmetry group and the stabilizer subgroup. And we'll see how that works. Or yeah, well, I'll just go over this very quickly, but just to sketch the idea. So before we defined a homogeneous space in a certain way, and then we saw, okay, it has this stabilizer subgroup. You can also start with a group and an arbitrary subgroup and construct a homogeneous space called a quotient space. There's some very subtle differences, but I won't go into that. So to understand this, you need this concept of a coset. And so a left coset of a subgroup H in the group G is a set of this form. Namely, it's the combination of our element G that defines the coset together with every possible element of H from our subgroup, capital H. So here you see a simple example. You have our group of symmetries of a triangle with flips and rotations, and we can consider the subgroup H consisting of flips, mirror transformations, so the identity and the mirror transformation, or the mirror combined with rotation, or R squared. What you see already here is the coset of the identity here. E times H is just H, and that's indicated by this green blob. And then there's two other cosets, one here and one here, and you can see that they partition the group. So every group element, E, M, MR squared, R, etc., is in one and exactly one coset. So the cosets, they kind of carve up your group into equivalence classes called cosets. And now the set of cosets is called the quotient. So if I start with this group with 6 elements, and then I forget about all the group elements, I just remember which cosets there are, I get, well, in this case, 3 cosets. And this space with 3 points is called the quotient space. In the case of SO3, you can think of it as somewhat like, topologically, it's somewhat like a sphere with a bunch of circles attached. So a rotation, you can think of it as indicated by an axis. That's a point on the sphere, and a rotation angle around that axis. And then these circles, you can think of those a little bit like the cosets. And if you take the quotient, you forget about the circles, you collapse them to a point, and as a result, you get the sphere. So you can think of the sphere as a quotient of SO3 by SO2. And yeah, you can show that the group G acts on this quotient space, and this action is transitive, and so indeed G over H is a homogeneous space, and that the stabilizer of this action is H, the group you quotiented by. So the high-level picture you can have in your mind is you have your group, it gets partitioned into these cosets. If you quotient them out, you get a quotient space that's a homogeneous space. Yeah, the group itself can be thought of as the homogeneous space, which at each level, at each point, a copy of your subgroup attached. All right, so that's the most important information if you're studying a homogeneous space, is what is the group of symmetries and what is the stabilizer subgroup, and then you basically know everything you need to know. So on this slide, I was going to take you through an example of how this applies to the case of sets, which is a homogeneous space for the permutation group. But in the interest of time, I'm going to skip that. It's still an interesting exercise to look at. So have a look at the handouts later. This also, I'm going to skip. Well, this is just to say that you can understand convolutional spheres in this way as well. Right, so in the last few minutes, I want to quickly give you the intuition for steerable CNNs and also the motivation for it. So let me see how to introduce this. So Let's say we have a signal on our homogeneous space, G over H, our quotient space. So let's say we're looking at the roto translation group again, and our signal lives on the plane. That's the roto translation group quotiented by the rotation group. And we have a scalar field, let's say a grayscale image. And now let's say we want to design a convolution layer that gives an output that's also a scalar signal. And we want it to be equivariant. Then you can see that the only way to do that is to use a circularly symmetric filter. Because if you use a non-circularly symmetric filter, if you rotate your image, you're going to get a different response. But since you want it to be a scalar signal, you can only use one filter. And so it should just be invariant to rotations. So that's one option. And the other option, okay, so the problem with this, of course, is that circularly symmetric filters are not very interesting. They don't allow you to detect very interesting kinds of patterns. Then on the other hand, you can use a completely free-form filter. But then, as we saw in the example of group convolutions, you have to apply every element of your group H to the filter. And that's fine if there's 4 rotations in the plane or 24 maybe in 3D. But if your group H is very large, then this means you get very many feature channels. And so what we're curious about is if there's anything in between those two, completely unconstrained filters, but having a lot of channels, or very constrained filters and having only one output channel. There should be something in between. And the way to understand this is via a certain concept called the induced representation. So the regular representation that we looked at is a special case of this. And the basic picture is that we have our homogeneous space with a stabilizer subgroup H, and we can look at a single point, and at that point we'll have a feature vector. In the case of the discrete rotations and translations, we had 4 orientation channels at each point. So it's a 4-dimensional vector, and it has a certain way of transforming. If we rotate it, we get a cyclic shift. And then the way the whole feature map, stack of feature maps transforms is that each of these columns, each of these feature vectors is rotated, and there's a cyclic shift. And that's an instance of an induced representation. So we have first a representation of our subgroup H, that's rho, in this case cyclic shifts, but it could be something else. And then from that you build a representation of your large group G that acts on fields of those 4-dimensional vectors in this case. Another extreme example is scalar fields. So if you have, say, an RGB image, the way it rotates is there's nothing going on the channels. It's just each channel independently is rotated. And so in this case, the representation of your rotation group acting on a single RGB vector is trivial. It doesn't do anything. That's another example of an induced representation. But there's something in between. So here you see an example of a vector field. You have your RGB image. You can compute, convolution with a spatial derivative filter. You get, an XY vector for each channel, red, green, and blue. And you can convince yourself if you rotate the image and then do the same operation, the two are related by, again, a rotation of each channel and a rotation among the channel vectors by 2x2 rotation matrix. And that's yet another example of an induced representation. It's another example. So the general picture is you have a group G, you have a subgroup H, and they together define a homogeneous space. You have a representation rho of your subgroup H that defines how your geometrical quantity is going to transform. Is it going to transform trivially as a scalar? Do you have a vector field, so 2-dimensional representation? Do you have a field of regular quantities where the dimension of your feature vector is equal to the size of your subgroup H or anything else? And then you have your induced representation that tells you how a field of such geometric quantities transforms. Yeah, that's the idea of an induced representation. And then you can ask, okay, maybe I have an input, let's say a scalar signal is here, and I want to output another scalar signal, or I want a vector field as output. What kind of equivariant linear map can I use? And the general answer that has been published under different names like Steerable CNNs, harmonic networks, tensor field networks, the general answer is that you should do a convolution where the filter is constrained in some way. So in the case of scalar to scalar, you would get these circularly symmetric filters, and in other cases you get other kinds of constraints. And this is universal again. So any equivariant linear map between two induced representations, between two spaces of fields, is on a homogeneous space is going to be a generalized convolution with such a constrained kernel. And the cool thing here is you can now classify a lot of different methods that you can find in the literature by saying what group do they use, what's the subgroup, which quotient space does that give, and what kind of feature types, what kind of representation do they use. So it's a very, very general framework that you can use to understand the whole literature on equivariant nets on homogeneous spaces. That's it. A little bit over time. Hope you you got something out of that. Yeah, happy to take any questions. Thanks for your attention.
Yes, hello. There are questions in campus wire, so I will read them.
Yes, please. I am in full screen mode, so I can't see that right now.
So you are in the you sign in campus wire, or I have to read the question for you?
No, yeah, sorry. I'll just take a second. I'm loading the page right now. Lectures channel, right?
Yes.
All right, so let's see, what's the first one?
The first one is the one of Mohammed. Is convolution a special case of group convolution?
Yes, I see. Yeah, that's exactly right. So the standard convolution that you find in in CNNs as first published by Jan LeCun in the I think the late 80s or early 90s, or before that in the neocognitron, if you want to be really precise about the history, those kinds of operations are indeed group convolutions for the special case where your signal is a function on Z2 on the grid, and your group is also Z2. It's the discrete translation group. And then yeah, you turn the crank, you use this whole general machinery, and out falls exactly this operation. So that operation of a translational convolution is indeed the most general kind of equivariant linear map for this particular situation. And for other groups and other homogeneous spaces, you get other kinds of convolutions, all of them being some variant of the group convolution or steerable convolution. All right, in the example with rotation, what is omega and c, and how is the signal defined? So, well, I covered different examples of rotation. So one is where you have a signal on the plane, and you're considering translations and planar rotations. And the other example is that you have a signal on the sphere, and you consider rotations of signals on the sphere. And so those correspond to different omegas. You can have your omega be the plane, either discretized, or you can mathematically also talk about a continuous plane, or continuous Euclidean space of higher dimension, like 3-dimensional. Or in the case of spherical CNNs, omega would be a sphere. As I also explained, in the higher layers of your convnet, after the first layer of group convolution, you would have the omega, the domain, be equal to your group. So, for example, you could have in the spherical CNNs, first layer is a signal on the sphere. Second layer, your signal is a function on the rotation group. But unless you use a rotationally symmetric filter, in which case you can take your output to also be a signal on the sphere. Now C, that's the channel dimension, and as with any convolutional net, also in group equivariant and steerable CNNs, you can just choose an arbitrary dimensionality for your channels. So in a standard convnet, at each position, you have a number of feature responses for different filters, and you can freely choose that. That's just a hyperparameter of your network design that will determine how many patterns can you detect, how many filters do you have, and also, of course, how many parameters you're going to have to learn. All right. So next question: in the case of convolution in the sphere, can we use UV mapping and continue with the normal convolution? All right, that's an excellent question, actually. And as an implementation trick, I think that you could do it. I should say, for those who are not aware, UV mapping is basically referring to parameterizing the sphere. So if you have a sphere, you could use, say, latitude and longitude coordinates. And then, just like a map of the world, you can plot it in a square or a rectangular piece of the plane, and then, well, you have a signal on the plane, and now you can do convolution on that. The problem with this is that this operation of taking a sphere and turning it into the plane doesn't respect the structure of the sphere. And it doesn't respect the symmetries. So first of all, it doesn't respect the topological structure, because you have to cut open the sphere in order to lay it flat on a piece of plane. And so 2 points that are very close together on the sphere, if you cut right between them, then they will be far away in the plane. And again, you could maybe do some hacks to get around that, like you could do a cyclic convolution. But the sphere has a very particular topology. So, for example, at the poles, if you make a cut like this, then the point at the pole will be represented in the whole top row of pixels. And so things go wrong topologically. That's first of all. And also, it doesn't respect the distances, because there's no way to turn a sphere into a plane without stretching or skewing the plane, or at least you're always going to lose some important geometrical information. And so what does that mean? Well, if I learn if I do this planarization and then I learn a square filter, as I'm shifting this filter translationally over the plane to do my convolution, that is going to actually correspond to a very weird kind of distortion of that filter on the sphere. So what you really want is you want one filter on the sphere, and you want to just rotate it over the sphere during your convolution, where, yeah, you really have the same pattern that you're detecting at different positions and orientations. But if you do it via this two-dimensional approach, implementation strategy, effectively you're going to be stretching your filter, and so that's undesirable, and that's why you would use the spherical CNN framework. And then question about B-spline CNNs. So basically, so this applies to Lie groups. So Lie groups are groups that are smooth. So it's a group that is also a smooth manifold where the group operations are smooth. The simple examples include continuous translations and rotations and scaling and such things. So you can do essentially calculus differentiation on your group. So that's where it applies. And then because so in a Lie group, there's something called the Lie algebra, which is basically, you can think of that as the tangent plane to your Lie group. So your Lie group is a manifold. You can think of it as a curved space. The simplest case, two-dimensional rotation, is just a circle. In the case of SO3, I tried to visualize it as a sphere with some circles on top. So a little bit misleading, but you know, you can think of it as some curved space. And any manifold, any smooth manifold has a tangent space at every point. So in the case of the circle, you can take a point and then you can draw the line tangent to the circle. That's the tangent space. In a higher dimensional manifold, you'll get a higher dimensional tangent space. And now there's a very nice way that you can parameterize the elements of your group by the elements of the tangent space at the identity. And that's what the B-spline CNN does. It defines a filter on this tangent space, which is a flat linear space, using something called a spline, and then it maps that to the group or the homogeneous space, and does a convolution that way. For details how to do that, you know, computationally, how to implement that, I would recommend looking at the paper. So that's it. That's the last question in Campus Wire. If anyone has other questions, also happy to answer those. If not, I have to go, because actually in 15 minutes I have to give another talk. So I would like to take another look at the slides. So if it's okay with you, I will stop sharing. And yeah, I'll see you soon at the next lecture, and I'll also be on Campus Wire to check if there's any further questions about this lecture.